All right, everyone. We'll do it live. Let us begin. So, here's my thought for today. So let's talk about today. Let's see, how many classes do we have left? I think we have today, we have Thursday, and then we have Tuesday. So today and Thursday, I think I'm going to do some graph stuff. We'll do the special topics this week. And so, what kind of special topics are we going to cover? Basically, I might do a little bit on disjoint sets, and then we'll cover graphs. And really, we're going to just do like maybe breadth first search, depth first search, A star, and Dijkstra. So those are the four like standard algorithms for searching a graph. And and that's how we'll do it. So disjoint sets are a little bit different. It's kind of it's a cute little application of a tree. And then maybe, so that's what we'll do this week. And then next Tuesday, we'll do final review. And then I will release the final. Maybe the 14th, maybe, the start of the finals day, or maybe the 13th. And then you'll have until the end of final exams to complete. Oh, there's two E's, I can't just do that. Final exams to finish. So that's the current plan. And the only difference between the final exam and exam 2 is basically going to be, well, the final exam will be cumulative, and it's going to include some basic stuff from maybe BFS, DFS kind of stuff. Just so that we can say that you've been given a slight... I promise you nothing that we're going to give you on this part is going to be very difficult, but it's basically some 441 practice. So that's the idea. Okay. So that's my current thinking, and I think that's all I really need to say about that. So let's get into disjoint sets a little bit. Let's talk about disjoint sets. So disjoint sets are kind of an interesting, they're kind of an oddball data structure, but as with almost all data structures, right? As with almost all data structures, they are secretly, how do you spell secret? Secretly trees. And that's the thing, right? So the only thing that really isn't secretly a tree, so hash tables are not secretly trees. At least not usually, not traditionally. I mean, maybe you could implement a hash table that's a tree somehow, but I'll say this, I've never seen a tree implementation of a hash table. So anyway, okay, so as with all data structures, they're secretly trees. So what does a disjoint set do? So what does a disjoint set do? Well, remember what the word disjoint means. It means that if you have two sets, I guess I should actually write this in LaTeX. Let's do that. It means that if you have two sets A and B, A intersection B is equal to the empty set. So that's what disjoint means, right? So if A and B are two sets, A and B are disjoint when A intersection B is equal to the empty set. And I'm just saying that again so that that'll give me time for the rendering to happen. Here we go. That's what disjoint means. So disjoint means that, again, you have two sets, their intersection, the little cap thing, is equal to the empty set. Cool, right? And you're like, well, okay, what's the point of this thing? The idea here is that a disjoint set is going to be some kind of object where we keep track, right, of, say, n different, or I don't could it even be more than n? Yeah, let's just say we keep track of objects, and those objects are going to, the thing is that all objects start out in their own set. So for instance, let's do an example where we have, say, the numbers 1, 2, 3, 4, 5. And you see here, I'm putting each number 1, 2, 3, 4, 5 in its own set. And so a disjoint union, the goal of a disjoint union is to track the union of these sets. Okay, so basically what you can do, for instance, let's say I union 2 and 3, so then what I'm going to end up with is if I union 2 and 3, what I'm going to end up with is 1 and then 2 and 3 become in the same set. And then let's union 4 and 5, right? And then, so what we're going to get is 4, 5, like this. And then finally what we're going to do, right? And here's the trick. Here's the trick. Goal thing about disjoint sets. We're going to union, say let's union 3 and 5 as elements, right? So we can't do that because they are actually in two separate sets. So we have two choices. We can either break 3 and 5 off and put them in new sets, which is not how disjoint unions work. Or the other option is, so we could, right, break them off, stick them in a new set. No, we're not going to do that. But what we're actually going to do, is pretend that they are representatives for their entire sets. And then we're going to union their sets. And so basically what we're going to end up with here is when we union 3 and 5, it'd be the same thing as if we unioned, say, 2 and 5 or 4 and 3 or whatever. We're going to end up with 2, 3, 4, 5 like this in a single set, and we're going to end up with 1 by itself in another set. So the question is, why is this a disjoint set? And the answer to that question is basically this. The answer to that question is, well, if you look at the distribution of all these different things, you see 1 is in its own set, 2 and 3, 4 and 5. If you take the intersection of any two of these, right, 4 intersection 5, that's empty, 2, 3 intersection 4, empty, 2, 3 intersection 5, empty. What would be an example of a non-disjoint set, right? The answer, why is this a disjoint set, is all elements are in exactly one set, right? And therefore, right, their intersections are all empty, right? So it doesn't matter which two that you intersect, their intersections are all empty, okay? So what are some applications of an idea like this? So we have this a disjoint set idea. So what, when might you want this kind of object? And this is a question that's more, this is less data structures and just more thinking about how the real world works. You think about things and you say, oh, well, if I'm picking people for teams, right? For instance, that's an example of disjoint sets. What's another example of disjoint sets? Another example of disjoint sets is, putting people into seats or on airplanes or something. If you try to say, okay, these people are going to take this flight and these people are going to take this flight. If you're like scheduling, say flights, each person, let's say each person is trying to get from A to B, the same start and destination. Each person is only going to take one flight, right? They're not going to take one flight from Baltimore to California and then they're going to get on another flight in Baltimore and go to California. Presumably they'd have to fly back or something like that. So is only on one flight. So if you were trying to schedule flights as in like try to put everybody onto a plane and make sure that there's enough seats for everybody, etc., that'd be one way to do it. You can understand that as a disjoint set. There's a lot of different things that you can understand as just disjoint sets. And basically the only rule, right, is that if you have two groups, right, say A group, group A, and group B, they can't share members, right? So if you ever have something where you're like, oh, well, let's make a bunch of committees, and as soon as someone, so for instance, here's not an example. if people are allowed to serve on 2 committees or more, right? So if they're allowed to serve on X committees, which is bigger than 2, then the answer is that's not a disjoint set, because the point is that if they were allowed to serve on 2 committees, then obviously Committee A and Committee B would share members or possibly share members, and therefore a disjoint union is not the correct object for that kind of situation. Okay, cool. So I think all of that's a pretty good understanding of kind of the idea of disjoint sets and how they work. Or I shouldn't say how they work, what they are, right? So now we talk about how they work. So how do we traditionally, and I should say traditionally in quotation marks, because it's not such a well-known data structure that you're going to say, oh, you know, from the 800 times I've implemented this thing before, you know, this is how I usually do it. But yeah, I'll say traditionally just because it feels nice. How do we traditionally implement this kind of structure? And the answer is, well, we're in data structures, right? So maybe a tree, right? Not a search tree, right? Not a search tree, but some kind of tree. And the answer to that is, yeah, yes. That's what we're going to do, okay? So you might say, wait a second, that's cheating because everything is a tree in this class. And the answer is, of course, everything is a tree. The only things that aren't trees are going to be graphs, which we'll talk about. And as you see, you'll see it actually goes the other way. Instead of all things are trees, you'll end up learning that all things are actually graphs. And yeah, so let's space these out evenly like this, and let's put some numbers in them. And let me show you how we can. Here's the idea of how we can change this into a tree structure. And so you're like, well, okay, this is not currently a tree structure. Help me out. And so I'm like, yeah, it's not exactly a tree structure right now. But remember what I'm going to do is I'm going to talk about representatives. So let's do the same kind of union operation that we did before. Let's union 2 and 3. So what I'm going to do here is I'm going to say, okay, if I union 2 and 3, so there's no real preference for who gets to be whose child. But generally what you're going to do is if you say union 2 and 3, then 3 will become 2's child, like this. And here we are. There we go. And then the next thing you do is you union 4 and 5. So let's do that. So we're going to union 4 and 5 like this. And so then the last thing what we're going to do is, remember, we're going to union 2 and 4 or 3 and 5, 3 and 4, something like that. Whatever. So the answer is here. So here's the trick, right? 2 is the representative of 3. 2 is also the rep of 2, okay? So, and then you know that 4 is the representative of 4, and 5 is, I'm sorry, I keep doing this backwards. 4 is the representative of 5, right? So what you're going to do in order to union these two things together is you're going to do this. You're going to say, all right, say I try to union 3 and 4 together. So normally what you would do is you would say, okay, I'm going to make 4 the child of 3, but then you start to see this kind of bad behavior here, right? You start to see this like long chain. It's kind of like a linked list, right? So if you union, say, 3 into 2, and then 4 into 3, and then 5 into 4, and then 6 into 5, and you go on like that, you're probably going to end up with some kind of linked list structure, and you don't want that. So basically what you're going to do, instead of linking 4 up onto 3 like this and have it also be a child there, what you're going to do is you're going to say, oh, okay, I'm not going to link it together with the number that I'm actually merging it with. I'm going to link it together with its representative. So for instance, here, I'm going to say I'm going to link 2 with 4, like that. And so that's how you do it, okay? And now there's some performance improvements you can do, but this is the basic idea, right? Basic idea. The basic idea is when you you union two sets, you make one set's representative the child of the other set's representative. Okay? So that's what you do. And then there's a little performance improvement that you can do, but we'll talk about that in just a second. So I think maybe at this point, we got the basic idea. I think we should actually just implement this thing. Let's try to implement it real quick. So let's create a new project. Let's call the project, say, Disjoint and Graph 21. Yeah, let's call it that, just so that it's unique. So let's open it in a new window. Okay. So let's see here. What are we going to do? Let's make a class called Disjoint Union. Python file. This is C-line. I don't believe in Python. There we go. Now it's showing me all the options. Okay, so let's make ourselves something like this. Let's say, what am I doing? Disjoint Union. Okay. So what kind of things does a disjoint union do? A disjoint union yeah, sure, we'll fix it. Hang on. It's gonna go blank for a second. There we go. Sorry about that. Okay. So, now that we're back to the land of the living, what does a disjoint union do, right? So it's going to, we're gonna have a union, right? Oh, I guess union is a keyword. Forgot about that. So, maybe we'll say set union. That way we'll and maybe, I don't know, maybe we'll turn a bool just in case it works. So we'll say int first rep, int second rep. So we'll get the two representatives and we'll do something like that. Okay. And then what else are we going to do? So we will say, and remember, once you union, so technically the data structure doesn't have the ability to pull things apart. You can always do that just by remove. So it's a little complicated, really, actually, to remove something, because if you think about it, like, how would you, in principle, like, what would you do to remove something like 4 from a disjoint union? What you'd have to do is you'd have to go through all of 4's children, relink all the children into 2, and then remove 4 and put it back in its own thing. So that's kind of something that we don't usually talk about. I mean, in fact, I've never really thought about it before, but I guess that's how you'd have to do it, right? Generally, the disjoint union is kind of considered like a one-way object. You can only stick things into the disjoint union. You can't really pull things out of the disjoint union. So now let's create like a display method. Yep, and that'll be fine. And then let's create a constructor. And then let's say int num elements, okay? And then here what we'll do is we'll say, and so this will have a fixed number of elements. You can always make it have more or less, basically, if you have a vector or something like that. Let's call it this union node. All right, so we'll need a node type. The node type is, I guess maybe instead we'll make it a struct rather than a class, because we just want everything to be public. So what is a union node going to have? A union node is going to have a vector of children. So what you'll have is a vector of union node pointer children, like this. And then you'll have int, say, value. And then you'll have some kind of constructor, I guess, right? The constructor will just set int new value, and let's just say the new value is equal to 0, but hopefully we never actually execute that code because that would be a slight problem. Value, new value, something like that. Okay, so I think that would be fine, right? I think that's all we really need. And then here what we're going to do is, I guess we can just say union node pointer plist. And so we can just say plist equals new int num elements with absolutely no safety, in case they stick in negative elements or something like that. Oh, new int, no. New union node. Okay. And then we should initialize all of these to num elements, I++, something like that. We should initialize them all to be let's just say, well, actually, let's increment. Let's be anti-computer science for a second. Okay, there we go. And so now, basically, all we have to do here is when we set the union, yeah, let's implement all of it just up here. This is, I guess we can just do this. So, so what are we going to do? What we're going to do is we're going to say if we want to union the first thing and the second thing, then what we're going to do, why doesn't it like this? I never used, who cares? Okay. So, like, what are we going to do in this case? What we're going to do is we're going to say something like this. We're going to say that first we have to find the actual representative. So, first set, let's call it first set and second set of the first set object. And so, for instance here, we have an array of these union nodes, and right now none of them have any children, but let's say that they did have children. And also I think we need a union node pointer p rep. I don't know if we want to spell out representative all the time. Okay. So basically, representative is going to be the version of parent here, right? And so whenever we union two things together, we'll have to set the parent, but also add it to the child list. So let's do that. So let's say that the first, so let's say while, let's say plist at first set, let's see, dot representative is not equal to null pointer. So what are we doing here, right? What we're doing is we're saying, and let me type out what we're doing first, and then I'll ask the same question again. There we go. So what are we doing? And the answer is, while the plist first set has a representative that's not just null pointer, we're going to set the value for the first set equal to the representative's value, and then we're going to head up one level. So basically, imagine what we're doing here is we're starting at 5. And so 5 has a representative that's 4. So then we'll start out with something where it says 5, and then the next step it'll say 4, and then the next step it'll say 2. And then 2 doesn't have a representative, or I shouldn't say that. 2's representative is 2, but in the data structure, we basically say that the pointer to the representative is null pointer, which means that it's kind of pointing to itself. So, I think that's one safe, that's one way to do it. And so here we're going to go, while the first set's representative is not equal to null pointer, you're going to find that the first set is going to just keep going up and up and up you set it to the representative's value over and over and over until eventually you get up to the top representative, and that's when you stop. And so now we're going to do the same thing for second set, right? Everything is identical except we're going to do second set, right? Let's do this. And again, same reason, right? We want to find the two representatives. And now what we're going to do, now we're going to merge. So, okay, so how do we merge? What we're going to do is we're going to say, okay, set the first set, or I should say, second set's representative to first set. And then what else are we going to do? We are going to set first set, or I should say add second set into first set's children. Okay, so those are the two things we need to do. But first, we need to check. And so the first thing, the question is, what do we need to check? We need to check whether or not they actually maybe have the same representative, because remember, users are crazy. So users might do something like union 4 and 5, or 3 and 5, I mean, right? So here what you would do is you would say, 3's representative is 2, 5's representative is 4, 4's representative is 2. And then what you would do is you'd union 2 onto 2, so you'd end up setting some kind of loop pointer business if you didn't check that. So the first thing we want to check is that if, first set is not equal to second set. And what that's doing is it's just making sure that we're not accidentally unioning together. And then otherwise we're going to, let's say we return false otherwise. Here we'll return true if we can union the thing. I'm not doing Python, I have to make it true and false or lowercase in C++. There we go. So if first set is not equal to second set, why doesn't it like this? Statement can be simplified. Don't care. So that'll go away as soon as we actually put some code into here. So, all right, let's do this. So if the first set is not equal to the second set, then what we're going to do is we're going to say second set, or let's say plist at second set dot p representative is equal to, and unfortunately I think we have to do it this way because I didn't make them double pointers, I made them single pointers. So it's gonna not, so I think it's upset with me because it's like probably gonna be unable to convert from union node pointer to union node. So basically that just means we have to do this. We have to get the memory location and actually set it as a pointer. Technically we could do all of this without pointers and just have everything kind of working with values, but whatever, we'll use pointers. Okay. So this works. Now we have to add into first set's children, right? Dot children dot pushback. And what are we gonna push back? We are going to push back. We are going to push back plist second set, the memory location, right? The pointer location of that. So that's how we union everything together. So, all right, cool. Okay, and then I feel like we could actually make a different method, like a check sets, int first, int second. Well, actually, let's just make it second set and first set so we can copy and paste. And what this one is going to do is it's just going to find the representatives and return first set is equal to second set, like that. So I just want this just in case we need it. Okay, so now what do we do? Now the last thing we have to do is make a display method. So you see that a disjoint union really is, it's not a very complicated data structure here, right? And we can talk about its time complexity in just a little bit, and obviously there's some best cases, worst cases kind of stuff, time complexities that can happen. But for now, let's just make a display method. So what should the display method be? It's a good question. What should the display method be? Let's see. Is there a way to get C out? I think there is, right? With the width. Like padded. Because I want to, I forget what the command is to get padding. Iomanip. Okay. Okay. Let's include IOStream. There we go. Haven't done this in a long time. So let's make it 5. And the reason why I want to do this is just so that it looks a little bit better. So C out. Oh, you know what we need? This is just a dynamic list. We don't actually know its size. So let's, right? We don't actually even know its size. So let's make a size and make that equal to num elements. Okay? There we go. So, all right, let's see what we're gonna do here. So I think on the first line, what I want to do is output this, and then what we'll do is we'll just see out maybe I plus 1, and then we'll maybe we'll do it this way, and then we'll see out an end line at the end. Okay, that should be fine. And then I know that the most interesting thing you can possibly see is somebody just doing a bunch of C outs, but I think that unfortunately that's where we are. And then we'll just do the same thing again, only this time we will do something like this, and then we'll see out another end line, and then we will see out under it, we will see out the representative values. So let's, so if p list at I dot p representative, right, then we'll see out p list I dot p representative dot value, I guess. Something like that. And else, right, I guess we'll just see out something like top, right? Top means it's its own representative, so see out one line. All right, so I think that that'll help us understand what's going on here. I think. So let's make ourselves, so let's include the disjoint union. And let us make one. So let us, let's say that we're going to put 10 elements in to start, and then we'll just call it DJ. is disjoint, or auto. Wait, no, that's dumb. Can't do that. Okay, disjoint union. There we go. That's how we can do it. I was thinking Python again. So cn. Guess we need include iostream again. Include string using namespace std. And then we can cn. Let's make a string command. So there we go. And then while there we go. Let's make some kind of little test loop here. So let's make two integers into x and y. And so what we're going to do is say if cmd is equal to input, or no, union, and then else cmd is equal to test, and then I guess at the end we'll just display like that, and so we don't need display. So basically here we'll just say cn x, y, right, there we go. So now we're cnning two integers, and we'll just do dj dot set union x, y, cool. And then finally here we'll do cout dj dot check sets x, y. I think that might be all we need, right? I think that might be all we need. So let's run this thing and see how many errors we have, right? How many problems that we've created. So let's see. Let's test, say 3 and 2 and 5 just to get it to display. Ooh, whoops. Oops. So looks like things are sort of kind of working, except display. I think I must have put an end line. Didn't I? Did I? Ah, the end line's inside of the for loop, so now everything's going to look terrible. Okay. Let's try this again. Of course, that's adding 4 characters rather than that, so I'm not entirely sure. We'll have to see. Hopefully this will look okay. What did I make the command again? Oh, test, not check. 2 and 5. Ah. That is the, I think that's the false that's being outputted. Okay. Why is it not, that's a good question. Let's do it one last time. Okay, it's a little bit better. These two are aligned now, but it's not aligning this for some reason. Let's look at it again and just see what's going on here. Should this be done? Am I doing all of this backwards? Should it be done like this? I'm not sure. I guess we're about to find out. Yes. Okay, so that That fixed it. All right, so now let's union, let's say 3 and 5, and let's see what happens. So either it's going to union 3 and 5, or it's going to union 4 and 6. Let's see what it does. Yeah, so here you see, okay, so actually what we want to do here is we want to do something like that, so that everything is shifted down by 1. There we are. Okay. So let's union 3 and 5 again. So what you see here is that 5 has a parent now. Its parent is 3. So let's union, say, 4 and 7. And so you see here, 7 has a parent that is 4. So now let's union, say, 7 and 3. Let's see what happens when we do that. Or let's union 3 and 7. I don't know why I want to do it in ascending order, but it doesn't matter. So let's see what happens. So theoretically what should happen is that 7 has a parent of 4. So yeah, let's just see what happens. So yeah, let's see what happened here. So 5 was the top. So basically how this is working now is that 4 and 5 are both the children of 3, and 7 is the child of 4, right? So 7 is a child of 4, 5 is and 4 and 5 are a child of 3. So now let's union some more stuff. Let's union 9 and 10. So there we go. Let's union 8 and 9. Oh, 8 and 9. So like that. And so here what we see is kind of some bad behavior where what we're ending, so 8's child is, or I'm sorry, 8's child is 9, 9's child is 10. So we're ending up with a kind of a linked list structure there, but you know, whatever, it'll be fine. There's actually a way to fix this. So there's a way to undo the problem that this is causing, and I'll explain. I might not actually implement it, but I will definitely explain. I will definitely explain what it's doing. So let's union a few more things. Let's union, say 9 and say 5, and just see what happens. Ooh, a bug. I think, right? Is that a bug? I think it is. Yeah. That didn't work. Okay, so what's the problem? I guess we should fix the problem before we move on. So the problem is, I think, something that scared me. So what's the problem here? We're unioning 9 together with 5. So, see, 9 already had a parent. So hopefully the representative of 9 would have been 8. So it would have gone up to 8. And then 5 has a parent, which is 3. And so theoretically it should just union... So that's a good question. Why did that fail? I mean, clearly, I think, you know, since this data structure is so simple, I think the only possibility is really that we're getting stuck somehow in one of these loops, right? Like that's, I mean, there's only 2 loops and then these statements, and these statements, if anything, right, the whole point about these 2 statements is that they're going to either execute or cause a seg fault. They're never going to cause an infinite loop, right? So these 2 statements are good. The only things that could possibly be a problem are these statements here. So clearly there's some kind of bug here that is causing this to happen. let's see here. So while the representative is not null pointer, we will set the null the next one. And then same thing here. While the representative is not equal to null pointer, we will set the next one. Good question. What's the problem here? So there's clearly an infinite loop, right? So what's happening is that like some one of these is like setting itself to, we're getting a loop here, which should never really be possible. I'm trying to think of if there's an easy way to test whether or not. Let's try this again. Let's union 2 and 3, union 3 and 4. Oh, we already have it. Interesting, interesting. So what's the problem here? If we're unioning 2 and 3, that means 3 dot parent is equal to 2. If we're unioning 4 and 3, oh, I think it all has to do with this +1 business here. I think the values need to be I. Is that what's causing this? That would be a horrible and simple fix. So yeah, let's say we union 2 and 3. Now we're going to union, say, so we have an issue there where you say 3 is getting unioned on to 1, so there's some issues there. But then let's union 3 and 4. Okay, and then union, say, 4 and 5. Well, let's union 5 and 4 and see what happens. Interesting. So now I've caused a huge amount of problems. Lots and lots and lots of problems. Right, so somehow it's not 5 whose parent is 4, it's 2 whose parent is 4. Oh, but that makes sense. That makes sense. Okay, that'll fix this, and then I think maybe we're on the right track. So let's union 2 and 3. There we go, and then union, say, 3 and 4. Okay, and then union 5 and 4. Like that. And so here, what is the structure that we have? So let's think about the structure that we have. So we're unioning 2 and 3. So 3's parent is 2. 4's parent, remember, is the representative 3. So they're both sitting right under 2. And then we're unioning 5 and 4. So 5's representative. Oh, I see. So actually, if you think about it, so what this is doing is it's saying, remember, because 5 is going first, whatever the first one is becomes the total parent. So 2 has a representative now. 2 was the parent before. Its parent becomes 5. So let's union some more stuff together and just test it out. So union 8 and 9, union 9 and 10, union, and now let's do the real big one. So let's union, say, 5 and 8, or 5 and 9, and just, okay. So now everything's working. And let me show you why everything's working. Because here what we have is that 4's parent is 2, 3's parent is 2, 2's parent is 5, right? So that parent is 5, 10's parent is 8, 9's parent is 8, 8's parent is 5. So basically 2 and 8 are the children of 5. So if we drew this thing out, let's actually draw it out. What we have here is we have 5 is the big dude. We actually have this structure sitting under 5, like this. And then everything else is in their own sets. So we have this, and then we have 8 here, then we have 9 here, then we have 10 here, and that's the structure that's being created by this. Okay, so this is the current set, and you see why you have to kind of test this stuff out, because the issue is, like, a lot of times what will happen is that if you have 2 large sets that each have a representative, you have to make sure that the union will work in both directions. That you can union, say, 5 and 9, and then maybe you would want to redo this test case and do the union of, say, 9 and 5, and that way you could have both things union together properly. Okay, so as it turns out, the disjoint union, as I say, is it's a pretty simple little thought experiment that you basically just use the idea of a tree to track whether things are in the same set. So now let's check. I forget. Oh yeah, test. That's what test. Let's say test 3 and 9. And remember, this is just returning a Boolean, so the 1 is true. So now let's test 1 and 10. Should return 0. Yep, that's false. And the reason why it's false is because if you notice, 1 is in its own set. 5 is the top of a set. So if we say union 1 and 6, then union 6 and 7, right? Then everything's going to be inside of a set, and so we can check stuff like test 6 versus 3, right? And you see that that's, I mean, I should really have made this better output, but you see that it's producing a 0. The 0 is what cout is producing on a false, right? So that's good, because you see that 6 and 7 are under 1, and they're in their own set, and then everything else is kind of under 5, right? So 1 is a parent, and 5 is a parent. Or I should say 1 is a representative, and 5 is a representative, and all the other things are either in the set 1 or 5. So you can test, say, 1 and 6. Yep. You can test 6 and 7. Yep. Test, say, 2 and 10. Yep, and then you can, let's do one last false one. You can test, say, 6 or 7 and 10. And that should return 0. Yep, cool. So all of that's working. I would say that 80% of my problems were caused by me deciding that I wanted to actually one-index all this stuff. If I just literally zero-indexed all this stuff, then we wouldn't even have had that original bug. Like, all of the bugs were caused by me putting a +1 in here. So that just goes to show you that you should always just let things zero-index and never try to do this. I was just trying to do it for the sake of, like, display and the fact that it kind of looks a little bit better and all of that. But and then hopefully this will. Oh, I don't even think I freed the memory, did I? I don't have a destructor. No, I don't. Not that we're ever actually going to need it or anything, but we can just delete. There we go. Now now the 341 gods should be happy, right? Okay. So that's basically all I want to talk about in terms of disjoint unions. I think that it's an interesting little example. I will post this code to the GitHub because there won't be any project on it. You're never going to see this unless, of course, you see it in algorithms. So basically, the only time you're going to ever see this again is maybe 441. But again, it's one of these objects that, like, it's always cool to talk about because you never know, you know, you end up thinking that all of data structures is just trees and heaps and maybe a hash table there. But there are other, and of course you'll say, well, this is really just a tree disguised, which I say, yeah, I guess. Okay. So now let's talk about graphs. So up until this point, we've only really had 2 types of underlying data structures. We've had trees and arrays, right? And as it turns out, arrays are their own kind of thing, right? They're a contiguous block of memory. There's a lot of things about arrays. Arrays are special, right? They're contiguous blocks of RAM that are either statically or dynamically allocated. So arrays are pretty special objects. And then, of course, you would say, well, the other thing that we know about are trees, right? And so what do we know that trees do? So I've made you think about ternary trees, right? And the reason why I made you think about ternary trees is because the whole point of this class is that basically almost everything is a binary tree, right? You might say, oh, well, it's not always a binary search tree, right? Not always with the search property. But like anything that's not an array, at least in your life, has been a binary tree. And so my point is that there are other things in the universe. Whoa. There are other things in the universe, right? And you can develop a ternary tree, which is something where you say, instead of having one value, you can have two values, right? v1, v2. And then whenever something is, say, if it's less than v1, it goes to the right, or it goes to the left, I should say. And then if anything is between v1 and v2, it goes into the center. And if anything's bigger than v2, it goes to the right. And so it's kind of like a binary search tree, except all the mathematics, the funny thing about it is that all the mathematics change, right? And basically it just changes by a factor of, say, like log of 3 divided by log of 2, right? So some kind of log-based change factor. Which it doesn't, so the reason why you don't generally implement this kind of data structure is let's actually look at what that number is. So if we take 3 and log it, and then take divided by 2 and log that, and here's the number we see. So we see that basically a ternary tree is going to perform, and what do I mean by perform? What I mean is, like, if you have a set of data, the number of levels is going to be like 1.58 less for every level. So it's going to be, you decrease the amount of levels by a factor of 1.58 per level. So I don't know if that really justifies the added complexity, especially because a lot of the times you can kind of do tricks with binary search trees, right? Like so like AVL trees are great, right? They're a nice, simple, easy way to balance binary search trees and ensure really good log-based 2 performance. You can actually probably, I've never actually done it myself, but you can imagine a kind of rotation on a ternary tree. Say you have A1, A2, say you have B1, B2, say you have C1, C2, right? You know that all of these elements are, you could do some kind of rotation, for instance, if you did something like this where you said, what I'm going to do is I will take, so these B's are between V1 and V2, so you might actually have to do something kind of more surgical. You'd have to really think about it if you're going to do a rotation on a ternary tree, which is why we generally do rotations on AVL trees, which are binary. But anyway, so let's talk about graphs. So what is a graph? And the answer is we've been dealing with graphs all semester. The secret is that we've just been dealing with a subset of them, a very simplified specific subset of graphs, and that subset is called the set of trees. So every graph, or I shouldn't say this, no, every tree is a graph, but not every graph is a tree. So what's the difference, right? So every tree is a graph. Not every graph is a tree, right? And so if you remember your 203, this is an example of a failure of a converse, right? But the question is, okay, so what is a graph? And here's the answer. A graph is a set or it's really two sets. It's a pair of sets, and we usually call them V and E, like this, where V is equal to a set of vertices. So you would generally name the vertices like A, B, C, D, E, F, something like that. You might name them like X1, X2. Actually, you might can use LaTeX for that. You can say something like X1, X2, X3, X4 dots. Say X, 257, X 258 dots, X sub n. Something like this, right? So V is just a set. Ooh, I did something bad. What did I do? Bad LaTeX. So the set of vertices doesn't really convey any information. So vertices are literally just the numbers, right? So they're just, you can even think of them as like the values or something like that. So they're vertices, which is the set V, don't really contain any information, okay? They're just kind of like the underlying set that everything is built on. So what is E then? E is called the set of edges. You might also hear, so in computer science, you might also hear vertices called nodes. You can hear them called like points. You can hear them, there's basically anything like that, anything where you, so those are different words that people might use, and I might actually use just interchangeably for the next, I guess, 15 minutes and then the next day to describe vertices. Edges are generally edges, and there's not really a whole lot of distinction made in the definition of edges. So edges are equal to a set of, say, x, y, where x and y are in the set of vertices. And so it's not all of them, right? Some of the xy's, or xy's in the vertices. So let me draw out what I mean by this. So let's draw some circles. And so this is generally how you start to draw a graph. You just generally draw circles at random like this. And then you number them or label them or whatever. So let's label this one A, B, C, D, E, F, G, and it crashed. Wonderful. All right, well, at least I didn't lose too much. Let's make some circles again. Circle time. There we go. Spread these out a little bit. Okay. Whoa, way too small. I really don't want to do this for all of them. Okay. D, E, say F, G, H, I, and J. Okay. So here's all the vertices that we're going to have for our little graph. Right? So the vertices are all basically A, B, C, D, E, F, G, H, I, J. Right? So that's the set of vertices. And now here's the set of edges, okay? So we're going to do something like this, where we connect A to B. And then I'll talk about the two different types of graphs, directed and, say, undirected. So what I'm drawing here is an undirected graph, okay? So let's connect these just to... but just to have, you know, some happy stuff going on, happy little trees. Okay, so here's a graph. We would call this graph undirected, okay? And the reason why we would call this graph undirected is because we have a choice, right? Sorry about that. Okay, we have a choice. When we can either create these things with arrows. So let me show you an example of a directed graph. So an example of a directed graph would be almost everything can be the same, except that what's going to happen is that some of these are going to get arrows on them, right? So let's say that this, say this, right? I'm just doing it kind of at random, but so it might not make a very interesting graph in the end, but we're just going to have to accept that fact. Let's add a two-directional edge. Let's say this edge, let's say this, and then let's say that, right? And so then let's make this a, you know, one-directional edge. This will be a two-directional edge. Oh man, I'm getting tired of all this, but you get the point, right? So the point is that, like, I'm just randomly sort of adding arrows to one of the sides. And then here, the point is that if you do this, right, unlike in this graph, so in this graph, what's the difference between a directed and undirected graph? And so you say, well, the arrows, obviously, because you drew in arrows for the directed graph and it's not there in the undirected graph. But what does it really mean to be a directed graph? And the answer is that here, you can start out at A and you can go to B or C. Here, you can go to A and then back, or you can go to A to B, but then these edges are undirected, which means that it doesn't matter which direction you go along them. So you can go from A to B, and then you can actually go back from B to A. So that's the big difference between a directed graph and an undirected graph. So here, here you can get from anywhere to anywhere because this is a connected graph. Here you can't, even though it's a quasi, it's sort of a connected graph, right? There's a path that leads from D to most of the different nodes. So if you tried to get from, say, D to H, you could go, you know, D, E, F, H. But if you tried to get back to D, there's no way to do it because even if you were able to go here, you couldn't get to A. If you went to H, you could get to I, F, get to E. But then here you see the problem, right? There's no arrow that leads you back. Now we could add one, right? Maybe you don't like this because it, you know, insults your aesthetic preference. You want there to be an edge that kind of allows you to get back, right, in some way. But that's the point about a directed graph, is that not all of the edges are symmetric. So you can go from C to E, you can go from C to D, you can go from D to E, but you can't go back from E to C or D, right? You can't get back. So the difference, and so let me just say what the difference is in terms of the set theory. So the set theory is that if you have set E, which is equal to, say, some xy's, right? Remember, it's equal to some of the xy's, such that x and y are in the vertices, right? So that's the definition of edges. Here, for a directed set, what we know is that for a directed set, or I should say for a directed graph, we know that if xy is in the edges, then yx is in the edges. Okay? So that's the number one thing. And so the way that you would do this in an implementation for an undirected graph is that you would actually have, you know, you have some node structure. So you have some node structure. And so what does a node have in it, right? And so the answer is that it's going to have like a vector of children, right? well, let's say a vector of node pointer children like this, and it might have, you know, a string, its name, right, something like that. But then, so this is going to be true for both a directed and an undirected graph. So the node structure looks the same, but the difference is that for a directed thing, what you're going to do is you're going to say vertex 1.children dot, say, pushback, say v2, and that's a directed edge, right? This is an edge from v1 to v2, directed edge. And so you can't just do that. For an undirected graph, what you're going to have to do is v2.children dot pushback v1 as well, right? So that's the point. So to make this an undirected edge, so then you have basically every undirected edge is composed of two directed edges, right? And all of this makes a v1 like v2 undirected edge. And of course now I have to move that because it's totally unreadable. Okay. So in order to make any undirected edge on a graph, you need to make two directed edges. And that's really it. And so now you see the difference between a directed graph and an undirected graph. And so in the last few seconds before we end class and all that stuff, let's talk about, so, you know, these don't look like trees, right? So I told you that these are trees. And the answer is no, they're not. But trees are these, is actually the proper way to say it, right? And so if you think about it, why are these trees? And the answer is because in computer science, a tree is called a directed acyclic graph. And so, and you might say, why is a tree directed? And the answer is unless you have a parent pointer, right? The only things that a node has, nodes only have like a p left and a p right. And so they only have a left pointer and a right pointer. And given that, the left child doesn't actually know who its parent is, right? So generally, the left child, or also right child, they don't know who their parent is, right? So that's a problem. Does that make, you know, so basically the point is that that's why we, a lot of times you'll hear that a tree is equal to a directed acyclic graph. And so the graph part we understand, right? The graph part we understand because it's just a set of vertices and edges. Now the last word that we have to unpack is acyclic, right? What does acyclic mean? And so the idea here is that you notice here that even with a directed graph, so with an undirected graph, it's very hard not to have cycles, right? Because without, so you see that there's a cycle here where you would say go from C to D to E to C to D to E and around in this cycle. A cycle is literally just a path in a graph, right? It's a collection of vertices. It's saying first you go to E, then you go to J, then you go to I, then you go to F, and then you go back to E, right? That makes it a cycle. When the first thing in a cycle is the last thing in a cycle, that makes it a cycle. So a cycle is any path that starts and ends at the same place, right? So really, when we say acyclic, what we really mean is that a cyclic graph is a graph that contains cycles, and cycles are paths that start and end at the same place. Okay, so now that we know what a cyclic graph is, an acyclic graph is a graph that has no cycles, right? Acyclic means no cycles. Okay, so what does it mean for a tree to be acyclic? Like, how would a tree be acyclic? The answer is it's a little bit hard because obviously you would probably object to anything I draw with a cycle being a tree, but let me just draw some example of something that's kind of like a tree, almost. So you'd say, like, okay, and assume that these lines only go down so that I don't have to draw a whole bunch of arrows, right? So pretend that this is directed. And then I'm going to do one squirrely thing. I'm just going to say, can I do that? No, I don't want to do that. I want to do this, right? So this is the one squirrely thing I'm going to do. Right? So all the other arrows go down. Let's see if I can put them all on at the same time. Wonderful, that was great, wasn't that? So now this is a directed acyclic graph, except, right, it's almost a tree. The exception here, it's just not quite a tree. And the reason why is because you see that if you go down, say, to the right child, and then let's say that this is also the right child, or it could be the left child, it doesn't really matter, one of the children points back up to the root. And so then the problem is that now you have a cycle in this thing. And so if you try, the reason why we don't do this is, remember, if you tried to do insert or find, or any kind of traversal, right? You always say, well, if p right, then you do, you do something to my node right here dot p right, and so if here dot p right, the guarantee that we expect, right, the thing that we expected from this is that this is never anything higher up in the tree, because if this is allowed to go back up the tree, then the problem is that this could end up being kind of infinite recursion, or if you do it with a while loop, it'd be an infinite loop. So these kinds of things lead to infinite loops or recursion errors, right? Basically, a Stack Overflow errors, right? And so that's the problem, is that with a recursion, it doesn't really matter how you code it, whether or not you do it by recursion or whether or not you do it with loops. The point is that if you do it either way, then this cycle is going to cause all of your tree algorithms to break. This one cycle, right? Of course you say, well, if I just insert on the left, then I'm fine. The answer is yes. But then, of course, I would say, well, fine. I'll just make this happen over here, right? And now you're in the same problem, right? So the problem is that, like, if you're not guaranteed that any particular thing can just randomly lead back up the tree, then this is just a general graph at this point. It's a directed graph. It's just a general directed graph. It doesn't have any special structure anymore. So anyway, so the thing is that you would say, like, this thing here, this object here is a tree, no problem. This object here is a directed graph. And so that's why you say that a tree is a directed acyclic graph, because it's a directed graph that can't have any of these cycles. And there you go. And that's really what it is. And so so we've been dealing with graphs the whole time. The only thing is we've been dealing with the kind of special case, and I would say the nice case, right, of graphs. So I know I'm over time. The only thing I'll say is that next time what we'll discuss is we will discuss the idea of breadth first search and depth first search. So I should write depth first search, then breadth first search, and then maybe if we have time we'll discuss A star and we'll discuss Dijkstra algorithms. And so A star and Dijkstra are just two examples of how BFS and DFS can be reclaimed if you have edges with values. So we'll have to talk about weighted graphs next time. But anyway, so this is a good little introduction to graphs, right? Graphs are basically these structures, and we'll discuss about how to search them next time. All right, that's it. That is it. I think we're done. All right. Talk to you later.